Hello and welcome back. In today's video, we're overclocking the Intel Core i9-11980HK processor all the way up to 5.2 GHz using an YİNG motherboard and EK Quantum custom loop water cooling. I'm excited to bring you along this overclocking adventure for 3 reasons. First, I've never overclocked a Tiger Lake processor before. Second, I have in the past overclocked mobile CPUs, but this is the first one in a long while. Third, I've never used a non-Taiwanese motherboard before, and YİNG is a Chinese motherboard vendor. And lastly, the BIOS options actually give us quite a good overview on how Intel CPU overclocking works behind the scenes. So let's get started. The Intel Core i9-11980HK processor is the flagship model in Intel's 11th generation mobile core processor lineup, codenamed Tiger Lake. The Tiger Lake H 45-watt processors launched on May 11, 2021, about 9 months after introducing the first Tiger Lake mobile processors. Tiger Lake is a bit of an unusual architecture because it never made it to the DIY desktop market. Intel famously opted for Rocket Lake instead. Well, kind of. Intel did release 4 Tiger Lake B SKUs for system integrators, including a Core i9-11900KB, which ended up in the NUC 11 Extreme. Intel Tiger Lake is the successor of the 10th generation Ice Lake mobile processor. Ice Lake is also an architecture that never reached the mainstream desktop. However, unlike Tiger Lake, it did appear in the 3rd generation Xeon processor lineup for workstations and servers. Tiger Lake is built on the 10nm SuperFin process and thus falls between Ice Lake and Alder Lake regarding process technology. In a strict sense, we could say that it has P-cores, since the 8 P-cores feature the Willow Cove architecture, which makes it the direct predecessor of the Golden Cove architecture used for Alder Lake P-cores. Another distinct difference between Tiger Lake and the mainstream desktop CPUs is that it only comes in a BGA package, not LGA. So the CPU has to be soldered directly onto the motherboard rather than put into a processor socket. We'll talk a little bit more about that later in the video. The Core i9-11980HK processor has 8 cores with 16 threads. The base frequency is 2.6 GHz. The Turbo Boost 2.0 frequency is 4.9 GHz, and the Turbo Boost Max 3.0 boost frequency is 5 GHz. The maximum boost frequency gradually decreases from 5 GHz for up to 2 active cores to 4.5 GHz when all cores are active. The base TDP is 45 watt and the Turbo TDP is 109 watt. The TJ Max is 98 degrees Celsius. In this video, we will cover 3 overclocking strategies. First, we unleash the power limits governing the CPU performance. Second, we overclock the DDR4 memory. Third, we get into simple manual CPU core overclocking. However, before we get started, let's have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. YİNG is a Chinese motherboard vendor based in Shenzhen. Normally, that wouldn't catch my attention. However, they specialize in putting BGA mobile processors on desktop form factor motherboards. And when I saw they also put HK overclockable mobile processors on desktop motherboards, that caught my attention. Since BGA processors don't sit on top of a socket, their Z height will be much lower than a normal desktop processor. YİNG put a special heat spreader on top of the BGA CPU to maintain compatibility with most desktop coolers. For example, this motherboard is compatible with any LGA 1200 cooler. BIOS-wise, it's not much different from the motherboards we're all familiar with. Aside from the lack of nice-looking UEFI skin, many settings and options are available. In fact, there are probably more options available in this BIOS than we find on some of the big brand low-end motherboard products. I purchased my board directly from Taobao, where you can find most of the SKUs. They also have a website you can visit for more information. The Elmo Labs EFC-X9 is the bigger brother of the Elmo Labs EVC and EVC-SB that I've covered in many previous SkatterBencher videos. The EFC-X9 supports up to 9 independent PWM fans and can supply 4.5 amps per header or a maximum of 20 amps in total. Additionally, there are 2 external temperature sensor connectors plus an onboard ambient temperature and humidity sensor. There's also a dedicated EFC software to control the device. I also use the device to map the radiator fan curve to the water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before starting overclocking, however, we must first check the performance at default settings. The default Turbo Boost 2.0 parameters for the Core i9-11980HK are as follows. Here is the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running Prime 95 small FFTs with AVX512 enabled, the average CPU core clock is 3078 MHz with 0.903 volts. The average CPU temperature is 51 degrees Celsius. The ambient and water temperature is 25.6 and 30 degrees Celsius. The average CPU package power is 45.4 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU core clock is 3583 MHz with 0.951 volts. The average CPU temperature is 50 degrees Celsius. The ambient and water temperature is 25.8 and 29.6 degrees Celsius. The average CPU package power is 45.7 watts. Now let us try our first overclocking strategy. But before that, make sure to locate the clear CMOS pins. Shorting the clear CMOS pins will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. The clear CMOS pins are located at the bottom of the motherboard. In the first overclocking strategy, we will simply try to unleash the Turbo Boost 2.0 power limits to maximize the performance. Usually this would be effortless because most motherboard vendors provide this in one single BIOS option. However, things are slightly more difficult on this motherboard, as you'll see in a couple of minutes time. So I'll first explain how Turbo Boost 2.0 power limits will help us unleash more performance, and then I'll also dig a little bit deeper in how to configure it on this motherboard. Intel Turbo Boost 2.0 allows the processor to run faster than the base specification. It allows this when the processor is running below temperature, current, and power limitations. The ultimate advantage is of course that you'll get higher single-threaded and multi-threaded performance. Traditionally, when we talk about configuring Turbo Boost 2.0, we refer to the Turbo Boost algorithm, which works according to a proprietary EWMA formula. Usually, there are only 3 parameters to consider: PL1, PL2, and tau. Power limit 1 or PL1 is the threshold the average power will not exceed. Historically, this has always been set to Intel's advertised TDP. PL1 should not be set higher than the thermal solution cooling limit. Power limit 2 or PL2 is the maximum power the processor can use for a limited time. Tau, in seconds, is the time window for calculating the average power consumption. The CPU will reduce the CPU frequency if the average power consumed exceeds PL1. However, in addition to PL1 and PL2, we must consider a number of other Turbo Boost 2.0 parameters. These parameters include the system power limits, power delivery limits, and temperatures. In our case, we will specifically configure 3 additional parameters: PL4, VRTDC, and VRIMAX. Contrary to PL1, PL2, and PL3, PL4 is not a measured power limit, but an estimated power limit. The power limit triggers preemptively when the CPU power control unit projects an extreme short power surge beyond PL2 in the very next instant. It projects the power by calculating the potential peak power, or PPP, which is a value based on the component characteristics and the present operating frequency. When PPP exceeds PL4, the PCU will automatically set a lower frequency. This is the very same PL4 limit that I previously discussed in the ARC A380 graphics card overclocking guide. VRTDC is the average per rail current limit of the voltage regulator of the CPU cores. It is designed to match the CPU throttling behavior to the motherboard voltage regulator design. It's intended to gradually adjust the CPU frequency and voltage based on the capability of the voltage regulator. VRImax is the maximum current limit for the voltage regulator. Adjusting the power limits is, strictly speaking, not considered overclocking. And that's because we don't change any of the CPU's electrical, thermal, or frequency parameters. Intel provides the Turbo Boost 2.0 power limits as a guidance to system integrators and motherboard vendors. And that's just to ensure that their designs can meet the base specification of the processors. But as we all know, better motherboard designs and better thermal solutions can enable peak performance for longer. But don't take my word for it. A little bit later in the video, it will become very clear what separates overclocking and not overclocking on Intel CPUs. I will cover the BIOS configuration of the Turbo Boost 2.0 power limits in a minute, but first I want to show you how you can identify Turbo Boost power limit issues or constraints on your system. We can use hardware info to identify what is limiting our Turbo Boost 2.0 performance. The objective as an overclocker is to have the Turbo Boost performance limited only by the max turbo ratio limit. That is the maximum CPU ratio configured in the BIOS, and we can easily override that to achieve higher frequencies and performance. Let's see how things work in the real world. We use Prime95 to push the workload and track the performance behavior in hardware info. When the system is idle, we can see that max turbo limit is triggered. When we launch Prime95 with all cores enabled, we find that quickly the thermal event performance limiter is triggered due to the CPU temperature. Then we find that the PL1 performance limiter is active a few moments later. The solution for the latter is pretty simple. Increase the PL1 limit. We go into the BIOS and program it to the maximum value of 4095.875 watts. Then we rerun Prime95 and find that a new performance limiter is activated, PL2 or PL3. So we go back into the BIOS and program PL2 to its maximum value of 4095.875 watt. We rerun Prime95 and find that a new performance limiter is activated, electrical design point/other, which include ICC Max and PL4. So we go back into the BIOS and program ICC Max to its maximum value of 1023 amps. Then we rerun Prime95 and find that the same performance limiter is activated when we enable AVX. So we go back into the BIOS and program PL4 to its maximum value of 4095.875 watt. We rerun Prime95 and find that a new performance limiter is activated, VRTDC. So we go back into the BIOS and program TDC current limit to its maximum value of 4095.875 amps. After these changes, the only performance limiters still active are the thermal event, in case our CPU hits the TJ max, or max turbo limit. Now that we've reviewed the Turbo Boost 2.0 power limit configuration, let's jump into the BIOS. Upon entering the BIOS, go to the Advanced menu. Enter the Power and Performance submenu. Enter the CPU Power Management Control submenu. Enter the Config TDP Configurations submenu. Set power limit 1 to 4,095,875. Set power limit 2 to 4,095,875. Leave the Config TDP Configurations submenu. Enter the CPU VR Settings submenu. Enter the VCC-in VR Settings submenu. Set VR current limit to 1023. Set TDC current limit to 32,767. Leave the VCC-in VR Settings submenu. Leave the CPU VR Settings submenu. Set power limit 4 override to enabled. Set power limit 4 to 4,095,875. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Unleashing the Turbo Boost 2.0 power limits has the highest impact in power-constrained scenarios. Unsurprisingly, we see the largest performance gains in heavy multi-threaded workloads such as Cinebench R23 and V-Ray. We get a maximum performance improvement of plus 20.43% in Cinebench R23. When running Prime 95 small FFTs with AVX512 enabled, the average CPU core clock is 4248 MHz with 1.136 volts. The average CPU temperature is 93 degrees Celsius. The ambient and water temperature is 26.8 and 32.8 degrees Celsius. The average CPU package power is 118.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU core clock is 4489 MHz with 1.143 volts. The average CPU temperature is 74 degrees Celsius. The ambient and water temperature is 26.5 and 32 degrees Celsius. The average CPU package power is 92.9 watts. In our second overclocking strategy, we will overclock the memory to get better system performance. For this, I will in part rely on Intel XMP, but I'll also need to do some manual tuning. Intel Extreme Memory Profile is an Intel overclocking technology that lets you automatically overclock the system memory to get better performance. It's an extension of the JEDEC specification that allows memory vendors such as G.Skill to program higher performance, frequency, voltage, or timings onto the memory sticks. There are two types of XMP certification, XMP Ready and XMP Certified. You can find the list of XMP certified products on Intel's website. Intel XMP 1.0 was developed for DDR3 and was later superseded by XMP 2.0 for DDR4. With the launch of DDR5 memory, there's now also an XMP 3.0. Overclocking the memory on this motherboard isn't as straightforward as simply enabling XMP. That's not because the option isn't available, but because I cannot increase the memory frequency beyond DDR4 4000. And my kit is rated at DDR4 4266. I suspect that this is a limitation not of the motherboard, but of the CPU. However, I wasn't able to verify this. As Bolzoid has explained in his great series of videos about memory timings, a memory stick is a pretty dumb device. It's actually the memory controller inside the CPU that sets the memory frequency and timings. The memory controller is located in the system agent part of the CPU die. So naturally, we find the memory configuration options in the system agent BIOS menu. In this menu, I copy the settings from the XMP profile and program them as a custom profile. The only thing I do differently is set the memory ratio to 30, combined with a memory reference clock of 133 MHz that yields DDR4 4000. Configuring DDR4 4000 also sets gear 2, so the memory controller runs at half the memory frequency. Upon entering the BIOS, go to the Advanced menu. Enter the Power and Performance submenu. Enter the CPU Power Management Control submenu. Enter the Config TDP Configurations submenu. Set power limit 1 to 4,095,875. Set power limit 2 to 4,095,875. Leave the Config TDP Configurations submenu. Enter the CPU VR Settings submenu. Enter the VCC in VR Settings submenu. Set VR current limit to 1023. Set TDC current limit to 32,767. Leave the VCC in VR Settings submenu. Leave the CPU VR Settings submenu. Set power limit 4 override to enabled. Set power limit 4 to 4,095,875. Enter the CPU lock configurations submenu. Set CFG lock to disabled. Set overclocking lock to disabled. Leave the CPU lock configuration submenu. Leave the CPU Power Management Control submenu. Leave the Power and Performance submenu. Enter the Overclocking Performance menu. Set Overclocking Feature to enabled. Leave the Overclocking Performance menu. Go to the Chipset menu. Enter the System Agent SA Configuration submenu. Enter the Memory Configuration submenu. Enter the Memory submenu. Set memory profile to custom profile. Set memory reference clock to 133. Set memory ratio to 30. Set TCL to 19. Set TRCD TRP to 19. Set TRAS to 39. Set TCWL to 20. Set TFAW to 51. Set TREF1 to 16,381. Set TRFC to 735. Set TRRD to 0. Set TRTP to 12. Set TWR to 24. Set memory voltage to 1.4 volts. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Increasing the memory frequency from DDR4 2133 to DDR4 4000 significantly improves the performance in single-threaded and multi-threaded workloads. But the most impressive performance improvement is in the Tomb Raider game benchmark with an increase of plus 32.50%. I double-checked these performance figures and always got the same result. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU core clock is 4261 MHz with 1.139 volts. The average CPU temperature is 93 degrees Celsius. The ambient and water temperature is 25.2 and 32.2 degrees Celsius. The average CPU package power is 125.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU core clock is 4489 MHz with 1.15 volts. The average CPU temperature is 76 degrees Celsius. The ambient and water temperature is 26.4 and 32 degrees Celsius. The average CPU package power is 101.1 watts. In the third overclocking strategy, we will finally overclock the CPU cores. For this, I rely primarily on the Turbo Boost 2.0 ratio configuration and adaptive voltage mode. But I also have to explain a little bit about the Tiger Lake voltage and clocking topology, as well as Intel's toolkit. So strap in, this will take a while. The standard Tiger Lake platform has a 24 MHz crystal as reference clock to the PCH. The PCH will then generate 3 clocks: an adjustable 100 MHz reference clock for the CPU internal clock generator, a fixed 100 MHz CPU BCLK for the PCIe DMI and I/O, and a fixed 24 MHz frequency for the display engine. Tiger Lake also supports using an external clock generator for driving the CPU reference clock. Whichever way you get the 100 MHz BCLK, this clock is multiplied with specific ratios for each of the different parts inside the CPU. Each CPU core has its own PLL and can run at its own independent frequency. The ring frequency ties together the ring, last level cache, and cache box. The GT or graphics frequency is based on the same 100 MHz BCLK, but is first divided by 2 and then multiplied by the GT ratio. Surprisingly, it appears that the slice and unslice frequency can be controlled independently. The system agent ratio is either 4x, 8x, or 10x. Finally, the two memory controllers and system memory are driven by the same 100 MHz BCLK. However, it also supports 133 MHz as the base frequency. The memory controller drives the clock frequency for the system memory. The Tiger Lake memory controller supports two memory gears, Gear 1 and Gear 2. In Gear 1, the memory controller runs at the same frequency as the system memory. In Gear 2, the memory controller runs at half the system memory frequency. Tiger Lake uses a combination of fully integrated voltage regulators, Fiver, and motherboard voltage regulators, MBVR, for power management. Tiger Lake processors have 3 distinct motherboard voltage regulator inputs. The Fiver then manages the voltage provided to specific parts of the CPU. The end user can control some of these voltages. VCC-IN is the primary power source for the CPU. It provides the input power for most of the important parts inside the CPU, including each CPU core, the ring, and the integrated graphics. The default voltage is 1.8 volt. It can be controlled using ISFID via the PCU. Through Intel's overclocking toolkit, we have access to up to 10 power domains. VCC-IN AUX is an auxiliary power source for the CPU. It provides the input power to the I/O parts inside the CPU. The default voltage is 1.8 volt. It can be controlled by directly programming the voltage regulator. Through Intel's overclocking toolkit, we have access to some of the power domains. VDDQ2 is the third power source for the CPU. It provides the input power for the DRAM I/O part of the memory controller, and it can be controlled by directly programming the motherboard voltage regulator. In a previous video on this channel, I described the history of Intel's overclocking toolkit. That video was called "How is Alder Lake non-K overclocking even possible?" And in that video, long story short, I explained that Intel has developed and maintained something what they call the OC mailbox. And inside the OC mailbox are all the tools we use for Intel CPU overclocking. On Tiger Lake, the overclocking toolkit consists of the following tools. Most, but not all, overclocking tools are available through the BIOS options. For example, per-core voltage configuration is unavailable in the BIOS, but it can be accessed through XTU. Notably missing from the OC toolbox are prominent features we know from mainstream desktop, like advanced voltage offset, better known as the VF points, and overclocking thermal velocity boost, or OCTVB. We all know the Turbo Boost 2.0 technology from its impact on the power limits. But a second, very important part of Turbo Boost 2.0 is the ability to set CPU ratios based on the number of active cores. Turbo Boost 2.0 ratio configuration allows us to configure the overclock for different scenarios ranging from one active core to all active cores. That enables us to run some cores significantly faster than others when the conditions are right. Intel provides 8 registers to configure the Turbo Boost 2.0 ratio. For mainstream platforms where the top SKU has no more than 8 P-cores, like this Core i9-11980HK, these registers are configured from 1 active P-core to 8 active P-cores. However, on platforms with core counts beyond 8 cores, we can configure each register by target Turbo Boost ratio and the number of active cores. Note that configuring the turbo ratios based on an active core count is not the same as overclocking each core individually. When we configure a turbo ratio based on the active core count, we have the CPU change frequency based on the actual usage. So let's say, for example, there's 4 active cores. Well, then the CPU will decide which of the cores will run at the frequency that we set through the turbo ratio configuration. As an extension of the Intel Turbo Boost Max 3.0 technology, Intel also introduced a new tool in the overclockers toolkit called the per-core ratio limit. This tool allows us to limit the ratio of each core individually, and that opens up 2 new avenues for overclocking. First, it allows users to overclock each core and find its maximum stable frequency individually. Second, it allows users to set an aggressive bi-core usage overclock while constraining the worst cores. Like any previous Intel architecture, there are 2 main ways how we can configure the CPU core voltage: override mode and adaptive mode. Override mode specifies a single static voltage across all ratios. It is mainly used for extreme overclocking where stability at high frequencies is the only consideration. Adaptive mode is the standard mode of operation. In adaptive mode, the CPU relies on the factory-fused voltage frequency curves to set the appropriate voltage for a given ratio. When configuring an adaptive voltage, it is mapped against the OC ratio, the highest configured ratio. We'll get back to that in a minute. Since Tiger Lake uses Fiver to control the core voltage, we can only change the voltage by programming the CPU PCU through either the BIOS or specialized tools like XTU. We can specify a voltage offset for override and adaptive modes. Of course, this doesn't make much sense for override mode. If you set 1.15 volt with a plus 50 millivolt offset, you might as well set 1.2 volt, but it can be helpful in adaptive mode as you can offset the entire VF curve by up to 500 millivolt in both directions. Let's focus on the adaptive voltage mode configuration. When we set an adaptive voltage for a core, this voltage is mapped against the OC ratio. The OC ratio is the highest ratio configured for CPU cores across all settings and cores. When you leave everything at default, The default maximum turbo ratio determines the OC ratio. In the case of the Core i9-11980HK, that ratio would be 50x because of the Turbo Boost Max 3.0. The OC ratio equals the highest configured ratio if you overclock. Specific rules govern what adaptive voltage can be set. The voltage set for a given ratio n must be higher than or equal to the voltage set for ratio n-1. Suppose our 11980HK runs 50x at 1.4 volt. Setting the adaptive voltage, mapped to 50x, lower than 1.4 volt is pointless in that case. 50x always runs at 1.4 volt or higher. Usually biases may allow you to configure lower values. However, the CPU's internal mechanisms will override your configuration if it doesn't follow the rules. The adaptive voltage configured for any ratio below the maximum default ratio will be ignored. Take the same example of the 11980HK, specified to run 50x at 1.4 volt. If you try to configure all cores to 45x and set 1.1 volt, the CPU will ignore this because it has its own factory-fused target voltage for all ratios up to 50x and will use this voltage. You can only change the voltage of the OC ratio, which, as I mentioned before, on the 11980HK is 50x and up. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and that factory-fused voltage. Returning to our example of a 11980HK specified to run 50x at 1.4 volt. Let's say we manually configure the OC ratio to be 54x at 1.5 volt. The target voltage for ratios 53x, 52x, and 51x will now be interpolated between 1.4 volt and 1.5 volt. When we set a global adaptive voltage, it maps this to the OC ratio, which applies to all of our CPU cores. So for example, if we set a global adaptive voltage of 1.43 volt and an OC ratio of 52x, then the VF curve for each core inside our CPU has a VF point all the way up to 52x and 1.43 volt. Side note, as I mentioned before, there's also this per core ratio limit where we can specify the maximum allowed ratio for each core inside our CPU. Contrary to our intuition, this per core ratio limit doesn't define an OC ratio for each core, but just restricts the VF curve of a core. So for example, if we have a VF point at 52x and the adaptive voltage at 1.43 volt, if we set a per core ratio limit to 51x, then that curve remains identical, except for the core will not be able to use 52x. It will only go up to 51x. Now that we know everything about adaptive voltage mode and OC ratios, we can begin tuning the voltage for this overclocking strategy. The first thing we need to know, however, is what is the maximum voltage for the CPU at default. So I plotted the default voltage frequency curve for the CPU. As you can see from this graph, the maximum CPU ratio of 50x is mapped against 1.417 volt. So that would be our starting point for setting an adaptive voltage when overclocking. For entertainment purposes, I also plotted the VF curve against a bunch of other Intel CPUs to see how this Core i9-11980HK processor stacks up. Looking at the 10th gen Core i9-10850K and the 11th gen Core i9-11900K processors, both 40nm++, we can see that the VF curve is very similar to this 10nm superfin 11980HK. The main difference is perhaps a plus 100 MHz at an equal voltage in favor of 14nm++ at the very top end of the VF curve. However, as we know, the 11900K can reach frequencies up to 5.5 GHz, which this 11980HK cannot. So, given a similar curve and some challenges to achieve the desired peak frequencies, perhaps it was a good idea after all to launch Rocket Lake on desktop and keep Tiger Lake for mobile. When we compare 11th gen Tiger Lake with 10nm superfin and 12th generation Alder Lake with 10nm enhanced superfin, which we now have to call Intel 7, we find that near the top end of the VF curve, the 12th gen can achieve the same frequency with 120 mV less and achieve plus 500 MHz at the same voltage. This difference is even greater when we compare the 11980HK with the 13th generation Raptor Lake Halo SKU, the Core i9-13900KS. Raptor Lake uses an enhanced process node dubbed Intel 7 Ultra. Compared to Tiger Lake's 10nm Superfin, Raptor Lake achieves plus 900 MHz at the same voltage and requires 250 mV less for the same frequency. Anyway, let's return to the Core i9-11980HK processor. Since every core has its own factory-fused voltage frequency curve, I also had a look at the different voltages for each of the cores inside our CPU. The first thing to note is that every core seems to have a VF point mapped to 50x, even though only the two favored cores, Core 2 and Core 4, can boost to that frequency. Secondly, we also see quite a divergence in maximum voltage. Core 2 only requires 1.33 volt for 50x, while Core 0 needs 1.417 volt. Fortunately, our two favored cores have the lowest voltage requirement for 50x. As I mentioned, the global adaptive voltage will be programmed for every single of the cores. Since the highest voltage across all of our cores is 1.417 volt, that will be our starting points. For this overclocking strategy, I decided to use 1.43 volt as an adaptive voltage, since I feel that's already quite high for this CPU. Upon entering the BIOS, go to the Advanced menu. Enter the Power and Performance submenu. Enter the CPU Power Management Control submenu. Enter the View Configure Turbo Options submenu. Set 1-core, 2-core, and 3-core turbo ratio limit ratio override to 52. Set 4-core, 5-core, and 6-core turbo ratio limit override to 51. Set 7-core and 8-core turbo ratio limit ratio override to 50. Leave the View Configure Turbo Options submenu. Enter the Config TDP Configurations submenu. Set power limit 1 to 4,095,875. Set power limit 2 to 4,095,875. Leave the Config TDP Configurations submenu. Enter the CPU VR Settings submenu. Enter the VCCIN VR Settings submenu. Set VR current limit to 1023. Set TDC current limit to 32,767. Leave the VCCIN VR Settings submenu. Leave the CPU VR Settings submenu. Set power limit 4 override to enabled. Set power limit 4 to 4,095,875. Enter the CPU lock configuration submenu. Set CFG lock to disabled. Set overclocking lock to disabled. Leave the CPU lock configuration submenu. Leave the CPU Power Management Control submenu. Leave the Power and Performance submenu. Enter the Overclocking Performance menu. Set Overclocking feature to enabled. Set Fiver faults to disabled. Set Fiver efficiency to disabled. Set VCCIN max limit to 2400. Set VCCIN voltage override to 2300. Enter the processor submenu. Set per core ratio override to enabled. Set core max OC ratio to 52. Set core 0, 2, 3, 4, 5, 6, and 7 max ratio to 52. Set core 1 max ratio to 51. Set core voltage mode to adaptive. Set core extra turbo voltage to 1430. Leave the processor submenu. Leave the overclocking performance menu. Go to the chipset menu. Enter the system agent SA configuration submenu. Enter the memory configuration submenu. Enter the memory submenu. Set memory profile to custom profile. Set memory reference clock to 133. Set memory ratio to 30. Set TCL to 19. Set TRCD TRP to 19. Set TRAS to 39. Set TCWL to 20. Set TFAW to 51. Set TREF1 to 16,381. Set TRFC to 735. Set TRRD to 0. Set TRTP to 12. Set TWR to 24. Set memory voltage to 1.4 volts. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. The overclocking capabilities of this Tiger Lake CPU aren't great, and with only a marginal increase of 200 to 300 MHz for each core, we can't expect drastic performance improvements. We see the largest gains in multi-threaded benchmarks as we increase the all-core turbo ratio from 45x to 50x. We get a maximum performance increase in Tomb Raider with plus 32.92%. When running Prime 95 small FFTs with AVX 512 enabled, the average CPU core clock is 4151 MHz with 1.112 volts. The average CPU temperature is 94 degrees Celsius. The ambient and water temperature is 26.2 and 31.8 degrees Celsius. The average CPU package power is 121.6 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU core clock is 4568 MHz with 1.185 volts. The average CPU temperature is 95 degrees Celsius. The ambient and water temperature is 26.1 and 32.4 degrees Celsius. The average CPU package power is 125.8 watts. As I was trying out some new tactics for my next overclocking strategy, I realized there's not much I can do with this CPU. And that's for two reasons. First, it seems Tiger Lake does not scale particularly well in terms of reaching higher peak frequencies. While 7 out of the 8 cores could easily reach 5.2 GHz at 1.43 volt in my previous OC strategy, none can run 5.3 GHz stably, even with a significant increase in voltage. The highest frequency validation I could reach was 5.4 GHz with over 1.5 volt. Second, the thermal situation is not good. As you can see from the Prime 95 results, this configuration reaches TJ max at only 125 watt. By using the data from the EFC X9, we can see that the main issue is the heat transfer from the CPU die into the water loop. This thermal transfer issue translates into quite low all-core operating frequencies. In a non-AVX Prime 95 workload, the frequency drops from 5 GHz to 4.5 GHz, and in an AVX 512 workload, it drops even further to 4.15 GHz. The only way that we could hope to get better all-core performance is to alleviate those thermal issues. Undervolting, I can already hear you thinking, why not undervolt? Well, normally I'd say great idea, but after some quick testing, I found out that the undervolting potential is only 50 millivolt. That's not enough to make a substantial difference. The next step would be to have a look at the YÍNG CPU heat spreader and see if any optimizations can be made. Perhaps the contact with the CPU die isn't optimal, or perhaps we can change the thermal interface material, or maybe we can try direct die. I would still like to explore these options, but I will save them for a future video. Or perhaps it's just a matter of transistor density. There's not a lot of information available on the transistor density of Tiger Lake or the capabilities of the 10nm superfin process technology. So maybe the chip will hit the thermal limit no matter what cooling solution we throw at it. Either way, for those who would like to know what are the further tuning opportunities, here's a short list. Undervolting opportunities are available in the form of an adaptive voltage offset. As discussed earlier in the video, this adaptive voltage offset will apply to the entire voltage frequency curve of each CPU core. Unfortunately, there's no advanced voltage offset available. The advanced voltage offset we know better as VF points. Anyway, so fine-tuning the VF curve isn't really possible. And like I already said, the undervolting potential was only 50 millivolt. Just like on any other modern Intel processor, we can independently tune the frequency and the voltage of the ring. Now, because Tiger Lake uses Fiverr, it means that the ring voltage is also separate from the core voltage. And that's different from regular mainstream desktop architectures, like for example Raptor Lake, where the ring and the cores share the same VCC-IA voltage rail. There's a voltage frequency curve up to the maximum default ratio, which in this case is 40x. Frequencies beyond 4 GHz can be mapped against a configurable adaptive voltage, which works according to the same adaptive voltage rules for the CPU cores I explained earlier in the video. The factory fused maximum voltage and frequency for the ring is about 4 GHz at 1.028 volt. I was able to achieve 4.5 gigahertz at about 1.2 volt, but that did not really significantly improve my performance. A final topic for the performance tuning opportunities is AVX. Tiger Lake supports both AVX2 and AVX512 ratio offsets, but using them is a little bit counterintuitive. By default, the AVX offsets are 0, which means that there should not be any offset available. So in our previous overclocking strategy, where we have a maximum per core ratio of 52x, it means that our AVX performance should go all the way up to 5.2 gigahertz, right? But that's not quite the case. And actually, we've seen this before. We've seen this on Alder Lake as well. Here are the AVX tuning rules that you have to keep in mind. By default, the maximum ratio during an AVX workload is the Turbo Boost 2.0 ratio. Effectively, the AVX2 and AVX512 performance is limited to 4.5 GHz when all cores are active and 4.9 GHz when one core is active. The AVX ratio offset is applied for each core independently based on the per core ratio limit. That means setting an offset of -1 would result in a maximum AVX frequency of 4.9 GHz for the favored cores and 4.8 GHz for the non-favored cores. Increasing the per core ratio limit does not affect the maximum AVX frequency. The AVX offset is applied to the default per core ratio limits, not the manual configuration. Setting any ratio offset in the BIOS won't apply. However, if you change the AVX ratio at runtime, for example using XTU, they will become active. I presume this last point is a bug in the CPU microcode. We saw this issue when testing Alder Lake, and I showed its effect on benchmark performance in a video titled World's Fastest Alder Lake. Alright, let's wrap this up. I was very excited when I found this YİNG motherboard with the 11980HK mobile processor, and that's for two reasons. One, I've been looking for ways how I could overclock mobile processors, and two, I've never overclocked Tiger Lake before. So this YİNG motherboard with the embedded HK processor was like hitting two birds with one stone. Overclocking Tiger Lake was also an interesting overclocking journey. First of all, I was amazed that the motherboard offered so many options for overclocking. I presume that the YİNG engineers simply provide all the options that are available in the standard Intel BIOS rather than handpicking those that they want to expose to the end user. And as a result, this motherboard has a lot more options than what we sometimes find on the low-end board of more established motherboard brands. 为YİNG的伙伴们点个赞. Second, Tiger Lake certainly lags behind Alder Lake in terms of absolute maximum frequency. At default, 5 GHz already requires 1.4 volt, and I was barely able to increase it more than 200 MHz with 1.43 volt. That's with a highly binned Core i9 Tiger Lake, not with some i5. If you remember from my previous videos, even my Core i5-12400 Alder Lake CPU could do 5.3 GHz with 1.3 volt, and my Core i5-12600KF could do 5.5 GHz with 1.45 volt. Also, in terms of thermal density, this is probably the most challenging Intel architecture I've ever tried. We hit the TJ Max at a mere 125 watt. On regular mainstream desktop CPUs, usually we hit TJ Max at 300 watt or more. And as a result, the all-core frequency and all-core performance is severely limited, especially in AVX512 workloads. But all things considered, I would say that this is one of the most interesting projects I've undertaken on this channel. And I'm tempted to explore Tiger Lake further. Maybe try out figuring out how to solve these thermal issues by using a direct die or something like that. But there's also the integrated graphics that I always enjoy having a closer look at. And maybe, who knows, we can do even some liquid nitrogen overclocking at Elmo Labs. Anyway, that's it for today. I want to thank you for watching and the Patreons for the support. As per usual, I'll have a written version of this video up on my blog, and if you have any questions or comments, you can drop them in the comment section below. And yeah, that's it. See you next time.